Okay, so in class this week we've been looking at vectors, and the first thing I'd like to do in our first homework video is to define the scalar product of two vectors. Now, there's a hint in the name that we're looking at the scalar product. You should hopefully remember from class that a scalar is different to a vector in that a scalar is just a number, whereas a vector is an ordered pair of numbers. At the moment we're looking at 2, but of course there can be more. This scalar product is also known as the dot product, for reasons that will become clear later. Now let's start with some vectors. So let's have A being A1 and A2 as its two components, and B being B1 and B2 as its two components. So in class we looked at addition and subtraction of vectors. It shouldn't come as much of a surprise as we're looking here at a product that we're going to be multiplying these two vectors together. Now there are two ways of multiplying vectors together, and we're going to be looking at the first way, the scalar product. It's known as the dot product because to denote this type of multiplication between vectors, we write A dot B. There is the cross product, which comes later, where we use the cross symbol for multiplication. So A dot B is equal to A1, A2 multiplied by B1, B2. And all you need to do when you multiply two vectors together in the scalar product is multiply each component in A with the corresponding component in B, and then add them together. So we have A1 times B1 plus A2 times B2. And you'll notice that the answer that we get doesn't look very much like a vector. And that's because it isn't. Because these components are all numbers, our answer here, we're just multiplying some numbers together and then adding those numbers. And so you should realize now that the reason why this is called the scalar product is because your answer is a scalar, not a vector anymore. Let's do an example. So if this time, rather than A1 and A2, A is -1, 2, and B is -2, -6, let's say, and our question says find A dot B, then A dot B will be -1, 2 dot -2, -6, and we do the same as we did up here. We multiply these two together and then these two together and add the result. So these two multiplied together, -1 times -2, a minus times a minus gives us a positive result, so that's a 2. Positive 2 times -6 gives us -12, or -12. So we add -12 to our 2, which, as we know, is the same as taking 12 away, and we get -10. And that's our answer. A scalar, not a vector, as we expected. Let's just formalize this in a sentence. So the scalar, or dot product of two vectors always gives a scalar. And I'll underline that for emphasis, not a vector. And it's important to note for these scalar products that certain rules hold. So, for the scalar product, we have that A dot B is always equal to B dot A. That's our first rule that holds. And I could prove it for you if you wanted me to, but actually you could do it for yourselves. If you did A dot B and then B dot A, see if you come out with the same answer, just using an arbitrary pair of components for each one rather than concrete numbers. We also have that A plus B dotted with vector C is equal to A dot C plus B dot C. So this rule says that you can multiply out brackets that contain vectors. So, if C is a vector, then we just do A dot C plus B dot C. And again, using arbitrary components, you could work this out with some two-component vectors and see if you get the same answer for both. And also, we can manipulate scalars in a very similar way as we would with normal numbers. So if we had a scalar times a vector, and then we dotted that new vector that we got, so that multiple of A, with the vector B, that's the same as multiplying a scalar by the dot product or scalar product of A and B. So it doesn't matter which order you do your multiplication in if you have an expression like R A dot B. It doesn't matter if you do R times A first, or even indeed R times B first, or if you did A dot B and then multiplied by the R. It really doesn't matter which way round you do things. These are very similar rules to the rules that we use when we manipulate algebra, also standard calculations with numbers. So they're nothing new, it's just that now some of the elements of these rules have two components rather than one. So I'm going to do a couple of examples now. From the book, I'm going to do 11.36 D and I. I'm going to do 11.37 G, 11.38 and 11.42. As always, and these are on pages 211 to 212. As always, I recommend you pause the video, have a look at these exercises, try and do them yourself, and then come back, check with me, see if you get the same answer as me, see if you do it in the same way as I do. You'll learn much better that way. So I paused my recording for the moment to write out the exercises, so you didn't have to watch me do that. So let's do them together. 11.36 asks us to calculate A dot B for a series of vectors. So in this case we have A is -1, 1 and B is 1, -1. Now these are written as row vectors, but as we talked about in class, they can also be written as column vectors for the purpose of multiplication. I think it makes it slightly easier. Of course, you can just do it on the row where you multiply the first component by the first and the second by the second, and that be that, but I quite like doing it this way. So we have -1 times 1, which of course gives us -1 as our first component, plus 1 times -1, which of course again gives us -1. So we have -1, take away another 1, which gives us -2 as our scalar answer. 11.36 asks us to multiply these two vectors together. So we have 0 and 7/8 times 5/9 and 0. So if we multiply these top two together, 0 times anything is of course 0. I hope you didn't make the mistake of writing 5/9. And 7/8 times 0 is again 0. So we have 0 plus 0 is equal to 0. And this is quite a special case, and it has a special meaning, which we'll talk about in later classes. But just note that a dot b can be 0, and it can be something special. 11.37g asks us to do something with the scalar that we get at the end. So we have minus 3, 5 times 7, 2 plus 15, which is equal to minus 3 times 7 gives us minus 21, plus 5 times 2, which is 10, and then we have our plus 15 at the end. So we have minus 21 plus 25. It doesn't really matter which order you do the addition in. You should always come out with the answer 4 at the end. So, our final two questions. 11.38 gives us the answer, but not one of the components. So we know that a dot b is equal to a1 and 4 times 3 and minus 1, which is a1 times 3, which more normally in algebra we can write as 3a1. 4 times minus 1 gives us minus 4, and we know that is equal to 17. So we just need to solve a simple algebraic equation. So we can add 4, we know that 3a1 is equal to 21, and divide by 3, and we get a1 is equal to 7. Done. So, I have 4 minutes to do our final question. Let's see if we can do it. I've summarised it here. In the question, trader orders 3 of a certain item for 50 euros each, and he orders 125 of a second item for €1 each. And the question asks us, first of all, to create the vector S, which is simply both of the order quantities. So we'll have S is equal to 3, 1, 2, 5. And the vector P gives us both prices. So we have 50 and 1. Now, first of all, it asks us for the meaning of the dot product of S and P. And this is an interesting higher order thinking question. We're taking both the quantities and multiplying them by both the prices individually and adding that together. So what do we get? Well, what do we get if we multiply 3 times 50 here? 150 euros would be the total cost of ordering these 3 items, and 125 times 1 would give us the total cost of ordering these 125 items. So actually, the meaning of S dot P is the total order cost for all of the items. And this is somewhere where vectors can be quite handy. So what did the guy spend? S dot P is 3,125 times 50 and 1. We get 150 plus 125, which is 275. And we know that because this is going to be the total order cost, that this will be measured in euros. And we need to have this understanding to know what this scalar would be measured in. We need to have our context. So hopefully that shows you that sometimes vectors can be quite useful, because if we just had this information, writing out an equation not in terms of vectors for the total order cost would be much, much longer than just writing vector S dot vector P. So hopefully they were all okay. If you have any questions, as like last year, please either bring them to class, ask them in class. I prefer it that way, because then you can share your questions with others who may share the same question or didn't even know they had that question. Or you can always write me a note in your notes in your book, hand them in with everybody else, and I can answer them and take a look, and maybe I'll answer them in class as well if I think they'll be helpful for other people.